Hello everyone, and welcome to 7th grade Math Module 5, Statistics and Probability. In this video, we're looking at lessons 3 and 4, calculating probabilities for chance experiments with equally likely outcomes. Our learning goal is to make sure we can calculate probabilities of events for chance experiments that have equally likely outcomes. This will help us to master Standard 7 SP6, approximate the probability of chance event by collecting data on the chance processes that produce it and observing its long-run relative frequency, and predict the approximate relative frequency given the probability. 7SP7, develop a probability model and use it to find probabilities of events, compare probabilities from a model to observed frequencies. And 7SP8, find probabilities of compound events using organized lists, tables, tree diagrams, and simulations. In this lesson, we're going to be using the term sample space, which is a set of all the possible outcomes of an experiment. So if we were looking for the sample space of an experiment where we're flipping a coin, our sample space would be heads and tails, because those are the two possible outcomes. Some other terms we'll be using are experimental probability and theoretical probability. You're already familiar with experimental probability from our previous lesson, which is found by repeating an experiment and observing the outcomes. So to find experimental probability, we take the number of times an event occurred and divide it by the total number of trials. Theoretical probability is based on what is expected to happen based on our math. So we could take from our sample space our total number of favorable outcomes and then divide it by the total number of possible outcomes. Let's first just try to get some practice with the concept of sample space. So we're going to try here to list out our sample space for each of these situations. You can pause the video and try them on your own, listing out all the possible outcomes, and then check back with the video. So if we're rolling a number cube with the numbers 1 to 6 on its faces, our sample space would be all of the possible numbers we could roll, which in this case are 1, 2, 3, 4, 5, and 6. Sample space can get a little trickier with something like number 5 when selecting a letter from the word probability, because we do have letters that repeat inside of the word probability. We don't need to have those show up more than once in our sample space. In fact, all of our possible outcomes should only be listed once in our sample space. So our sample space for probability looks like the word probability, but we're missing our letters that are repeated. So it's just P-R-O-B-A-I-L-T-Y. We don't have to repeat the B or the I when they repeat in the word. Finally, for spinning our spinner, since each of those numbers shows up once, then all of the numbers on our spinner are a part of our sample space. So now that we've reviewed sample space, let's dig into some of the differences between experimental and theoretical probability. So your teacher has a bag with some cubes colored yellow, green, blue, and red. The cubes are identical except for their color. Your teacher will conduct a chance experiment by randomly drawing a cube with a replacement from the bag. Record the outcome of each draw in the table. So what happened is I took a bag full of these cubes and I pulled out 20 of them. Each time I pulled one out, I put it back in so that I still had the same chance each time I went to pull something else to get anything else out. So here are my results, and we're going to use these to try to calculate some probability. So I brought my results here, and based on these 20 trials, we're going to estimate the probability for each of the cube colors. Because it's talking about using the data from my trials, this is experimental probability. Since you're already familiar with this, you can pause the video and try to calculate the probability for each of the cubes on your own. So as we already mentioned for probability, to find the probability of any of these events occurring, all we need to do is take the number of times that event occurred and divide it by the total number of, in this case, trials. So for yellow, we had that there were 7 yellow out of the 20, so that's the probability of pulling yellow. For the green, there were 3 out of 20. For the red, there were 4 out of 20, which simplifies to 1/5. And for the blue, there were 6 out of 20, which simplifies to 3/10. So this here is our experimental probability. We can use our experimental probability then to make some inferences about how many cubes are in the bag. We also reviewed this in a previous lesson. So if there are 40 cubes in the bag, how many cubes of each color are in the bag? So I'm going to use my fact family triangle showing the relationship between that big P, our probability, the T, which is our total, and then the E, which was our event. So in this case, since we're looking to see how many of each color is in there, that's going to be our event. It's in that part space. And we're going to take the probability for each color and multiply it by the total number of cubes in the bag, which was 40. So you can pause the video here to try to calculate this on your own and then check back with the video. For yellow, I just take that probability of 7/20 and multiply it by my new total of 40. I've changed it into the decimal 35 hundredths and found that there should be 14 yellow cubes in the bag. For green, when I took the probability of 3/20, which is 15 hundredths as a decimal, and multiplied it by 40, I got that there should be 6 green cubes in the bag. For red, I took the probability of 4/20, which is 2/10 as a decimal, multiplied it by the total of 40 to find that there should be 8 red cubes in the bag. And then for blue, I took the probability of 6/20, which is 3/10 as a decimal, and multiplied it by 40, and found that there should be 12 cubes that are blue in our bag. So in this situation, we've made some inferences about how many are in our bag. And if I were to do this experiment again and draw another 20 cubes, and again putting them back in before I pull out the next one, I shouldn't expect to see the same exact results. Because this is something that is random, I can't assume that the first time I'm always going to get a red, the second time I'm always going to get a blue. I can't even assume that I'm going to get the same amounts of each color. So this is a really nice way of trying to make an inference based on what has happened, but it doesn't mean that's what's always going to happen because life is random. But now we are going to dig in and see what exactly was in that bag. How many of each color did I actually have? And I can compare it here with what I calculated. So what I actually had in each bag was I had an even amount of each color. 10 yellow, 10 green, 10 red, and 10 blue. If we look back at my estimations, I'm really not that far off. I do have 14 and 6 here, but if I really average these out, they do get us right back to that 10. So they're not exactly in line with what theoretically could have come out of my bag, but that's part of life being random. So to find this here, the theoretical probability from my bag, for any of these colors, I'd end up doing the same thing. I would take how many of my color I was looking at, which for each color is 10, out of the total number of cubes in the bag, which is 40, and that simplifies to 1/4 or 25 hundredths, 25%, when I'm changing it into my theoretical probability. So in theory, a quarter of what I pulled out of the bag should have been each color. Now, the interesting thing when we're looking at outcomes that have equally likely, just like it was equally likely for me to pull out any of these colors, the probability ends up simplifying to 1 out of the total number of possible outcomes. Since I had 4 colors in my sample space here, my probability for each of them, since they were equally likely, was 1 out of those 4 possible options. We're just going to wrap up with one more chance for you to try and figure out some theoretical probability. So an experiment consists of flipping a nickel and a dime. The first step in finding the theoretical probability of obtaining heads on the nickel and heads on the dime is to list out the sample space. So you can pause the video now to try to write out the possible outcomes, aka the sample space, for flipping a nickel and then flipping a dime. So when I'm trying to make my sample space for a compound event like this where 2 different things are happening, I find it helpful to draw something called a tree diagram. So what happens in a tree diagram is I list out all the possible outcomes from my first event, and then I branch off of it all of my possible outcomes for my second event, and there's a set of branches with all the possible outcomes for each of the outcomes in the first one. So heads for the nickel got both the heads and tails for the dime, as did tails for the nickel. So I can take this tree and then I can turn it into a sample space, which would be heads heads, heads tails, tails heads, and tails tails. So now that we have a sample space, you can pause the video here to try to find the theoretical probability of flipping two heads. So we don't need to flip any coins for this, we just take our sample space and what we're looking for and use those to make our probability. So we saw here that there was only one outcome that had heads on the nickel followed by heads on the dime. So we take that event and divide it by the total number of possible outcomes in our sample space, and we get the probability of 1/4, which is 25 hundredths or 25%. What does this make you wonder about theoretical probability and the relationship between experimental and theoretical probability? Write your questions down so you don't forget them. Then you can try to find answers online or ask a classmate or teacher. Thanks for watching, and when you're trying this on your own, remember, if you learned from your failures, then you succeeded.